Hey everybody. So let's discuss the whole problem-solving technique I've been mentioning using conservation of energy. So that's where we bring together everything we've learned about work, kinetic energy, potential energy, all of that. So let's start off with the work energy theorem. That's the one, work equals the change in kinetic energy. But this work is due to force. But then you can have different forces such as, let's say, non-conservative forces and conservative forces, of which we've talked about two of them, gravity and springs. Right? So if you have work by a conservative force, it's equal to minus the change in potential energy, right? Work by conservative force equals minus the change in potential energy. And let me just jot on the side. We know potential energy for gravity is like weight times height above a datum of your choice. Potential energy for a spring looks like 1/2 kx squared, where x is just the displacement from the unstretched position. Okay, so we know two of these right here, potential energy. Now, if we take a look at this, let's move this on the other side. Okay, and what happens is we can bundle together kinetic energy and potential energy, and we'll just call it mechanical energy. We'll call it E, mechanical energy. So mechanical energy is kinetic energy plus potential energy. Okay, and then here we go. We can start our problem solving here. Let me just write it in a different way, which I think is easier to explain to other people. So this means final minus initial. Final minus initial. And I'm just going to bring this on the other side of the equation. So work by non-conservative forces. And then I'll bring this on the left side of the equation. Initial. Final. And make a note that if there are no non-conservative forces, we can just cross this out. And look, the initial energy equals the final energy, meaning the energy is constant, or we say conserved. But if there are non-conservative forces, then it does work and it ruins our nice conservation here where the energy stays the same. And I always think of it like, say you have a bank and you have different accounts within your bank, checking account, savings account, Christmas savings account, and it's like there's kinetic energy, let's say gravitational potential energy, spring potential energy. So imagine you can take money from one account and put it to another account. Like take 10 bucks out of this one and put it here. Take $5 out of this one and put it here. Or, you can move like this. You can move money between the accounts. The total amount of money in the bank stays the same. So that's exactly what's happening here. Energy can change forms, but the total amount stays the same unless you come along and withdraw money from the bank or deposit money into the bank. And that's what this is. Okay, so one example of a non-conservative force that does work is friction. So let's do a few practice problems like that. So let's start with maybe a straightforward one. Here's a block. And let's say this is smooth for now. And let's say you release this from rest. And it slides down the ramp and then it's down over here. And let's say this is some distance d. Okay, how fast is it going over here? So you know how to do this using Newton's way, right? You draw the free body diagram, right? Newton's laws, then you solve some kinematics. let's try this energy way now. Okay, so it's smooth, so we don't have any friction. So for this particular example, this is 0. Okay, so initially, how much energy do we have here? What is the kinetic energy? I'll just write it over. Let me write it over here. Initial, final. Initially, over here, how much kinetic energy? 0, right? It's at rest. So I'll write it and I'll just cross it out. You don't have to write it and cross it out, just I'm explaining, right? Okay, how much spring potential energy? 0. There's not even a spring, so maybe I don't even have to write that. How much gravitational potential energy? mgh. H what though? The height above the datum of your choice. Where would you like to choose the datum? Here? 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 Any choice is fine. So totally up to you. Let's say I choose the datum here. Here's my datum. One possible of infinity choices. So what is the height above the datum? mgh, where this is the height above the datum. For this particular example, that height would be d sine theta. Okay, so that's the potential energy, gravitational potential energy, and then that's it. We're done on this side of the equation. Now this side of the equation, final, here. What is the kinetic energy? 1/2 mv squared for this speed v. Okay, what is the spring potential energy? There's no spring, so none. What's the gravitational potential energy? mg, the height above the datum. It's at the datum, so the height above the datum is 0. So mgh, the final height above the datum is 0. So that's it. So that's all we got. If we know this distance, this mass, this angle, the only unknown is the speed here. So we got our one equation, one unknown, solve for the speed. 2g, there we go. Okay, let's try the same problem, but this time, let's say there's friction. And then let's say the coefficient of kinetic friction is given, mu k. Okay, so how much work is being done by friction? In this case, this is going to be work by friction. Okay, how much work is being done by friction? Now we kind of need to do all of this business, right? The free body diagram. Normal force, friction is going opposing the motion. If I pick coordinates, let's say like this, then the angle is here. So in the x direction, we got mg sine minus friction, mass times acceleration. In the y direction, we got n minus mg cosine equals mass times acceleration. If the block is going this way in the x direction, then there is no acceleration in y, so this is 0. Not always true, just because of the way I pick my coordinates. So look at this, n equals mg cosine theta, which means I can solve for friction. Friction is mu k times n, so mu k mg cosine theta. Now what is the work by friction? Friction is a force going this way. The displacement is this way. So what is the dot product? They happen to be exactly kind of 180 degrees from each other. So the work by friction is going to be this dot this, which is exactly minus that friction force times this displacement. Right, that's the work by friction. Okay, and then we can fill in the blanks where friction is this right there. So we got it, right? We got it. It's UK mg cosine theta times d. I'm going to move the d over here because I kind of write sloppy sometimes. So cosine theta times d. That's what I mean to write, not cosine of theta times d. That's not what I mean. So to not mix it up, if I move the d on this side, d cosine theta, then it's clearer, right? I don't mean this. So that's why you'll sometimes see me write it like that. I always write it like that. Okay, so that's this right here. And then the rest of it is exactly like before. But how about this time? What if we pick the datum here? Okay, what is the initial kinetic energy? 0. 0. It's not moving. What is the initial potential energy? Gravitational potential energy. mgh above the datum. It's at the datum, so that's 0. Okay, so we're done here. Final. Here now, what's the kinetic energy? 1/2 mv squared. This is our unknown. What's the gravitational potential energy? mg height above the datum. It's below the datum. So negative this much. For this geometry, that's d sine theta. Okay, so there's the minus sign here because it's below the datum. And here we go. We got one equation, one unknown. Solve for that speed, you got it. Okay, so this is the method we'll use from this point. And if you notice, if you compare it to if you did Newton's way, that way would be not so bad, but more time consuming. So practice this method and let me know if you have questions. I can provide more examples and post videos of more examples. So I'll see you on those videos.